Thank you for the reminder.
You're welcome, sir.
Okay, so pro- protocol stack helps you to split the activities in an organized way, because in networking you have the processes in some orders. Okay, one has to be done before you do another process. So it's better that you put them in some layers. Secondly, this sort of layering, or I mean the processes that you handle uh, for different types of operation in the order have some commonality uh, among all sorts of networking. This is why some 7-layer model concept is in use, and the basic concept of this model is termed as OSI model. Uh, I I'm not okay. Maybe I just write down this term OSI model, uh, but we won't really be specific to that model because different variants are used for different. I'm just writing in the chat box. I'm writing
Sir,
down that generic term OSI
OSI,
model. Yeah, go ahead,
sir,
please.
OSI model was covered in our data communication networking one course
Okay. Oh,
and
very good.
TCP/IP protocol.
Okay, TCP/IP protocols have also been covered,
Yes, sir.
you say? Oh,
Yes,
very
sir.
good. And did you cover IP version 6 or 4?
IP version 4, IP
Okay.
version 6 was. So as far as I know, the only difference is the length of the address.
Address, yeah, I mean, pretty much like that. And you can have uh, the MAC address actually built in the case of IP version 6. Okay. I mean, it's a part of your whole IP version. Like if you use, say, Ethernet, you are given a MAC address, and the IP version 6, the MAC address is 48 bits long. Okay, for Ethernet, the Ethernet card comes with a unique 48 bits long MAC address, and when a IP address is generated in version 6, then these 48 bits become a part of that 128 bits. Okay, so that's basically the beauty. You have some property inbuilt within that whole long address. Okay. Anyway, so that's a relief for us. Very good. So in our case, it will be a variant of OSI model, and you have that. You can see the slide, right? Can you?
Yes, sir.
Okay. So layer 1, you have the layering on the two sides, both on transmission and reception sides, and in uplink, the UE is the transmitter, the node is the receiver. On the network side is the receiver. The downlink is the other way around. Uh, but this layering remains the same, and so we can just show them uh, on the two sides for either uplink and downlink. And so it's like this, that you have on the UE side, you have, so you have just two sides, network side and your phone side. Okay, the network side has different components, but on the phone side is only the phone. So all the 7 layers will be put together on the phone side, but on the network side you have the provision for splitting some layer in some nodes, some other layers in some other nodes. Okay. Now on the phone side, all the layers, all the 7 layers are not shown here, but the ones that you primarily you basically connect to the network side are shown here. And it is shown here for user plane, meaning that we had earlier consideration of 2 separate paths for your for uh, handling purpose, like how you handle the how handle all the activities. Like you have your user data that is routed this way, and secondly there are a lot of control, okay, all the time between the phone and the network, and so this is a different path for that. Okay, maybe straight path for just routing your user data. So you, when you think of the activities, you also think them separately. This is also a beauty that you have in 4G. In 2G or 3G, things are not organized this way. You don't have control and data routing components separated in core network. It wasn't there in 2G or 3G. Now they separated it. In 2G or 3G, if you look at, we didn't show the architecture network. This whole thing is called network architecture. The way you put the components in the network is called network architecture. If you look at the network architecture for 2G or 3G, you can just go online and check. You'll find also 2 different components in the core network, 2 different paths on the core network. But those 2 paths are for CS and PS, circuit switching and packet switching. You know that in 2G and 3G we had these 2 different uh, categories or types of processes. But here you have all IP, all PS. Okay, so there is no CS, but again you have 2 different paths, and that allows you to separate control and data. Okay, so the protocol stack is also considered separately for. This was also separate for 2G, 3G, but it is more organized here because of the separate components in the core network. You also had control plane protocol stack, user plane protocol stack, okay, in 2G or 3G, but in terms of components, you have it more organized. Okay, the way we can show it in a better way here. Like in the core network, you have separate components for user plane. You have one kind of components here for user plane, and different component for control plane. In control plane, you have behind the E node B, the MME. Okay. And here you have the serving gateway and PDN gateway. Okay. For control, you have the MME component, and for user plane, you have behind. This is just E node B, just the base station. That's it. You have serving gateway and PDN gateway. Then is the network cloud, internet cloud. Okay. For user plane, the layers in the protocol stack are physical layer or layer 1. Then layer 2 has 3 different parts: MAC, RLC, and PDCP. Okay. And in data networking course, it also has a second part. So maybe many of you may be taking that course. So there are few different IEEE protocols you may be covering there. And what you should find there in layer 2, IEEE doesn't specify anything above layer 2. Their specifications lie within layer 2, layer 1 and layer 2. So they specify everything. And in layer 2, they use MAC. So they have physical layer and MAC layer to actually specify all different types of protocols. Okay, so that is what you should find there to handle using layer 1 physical layer and layer 2. But here you make things better organized. You have many different kinds of processes, and it is a okay. Let me just tell you that WiMAX is very similar with our mobile. I mean, that's another type of mobile communication technology, right? So you have similar kinds of activities, but I mean, they have just layer 1 and layer 2, MAC layer and physical layer. So things are not that well organized. They have so many processes, but using just these 2 layers, so it is difficult. I actually had to learn WiMAX quite a bit, and so yeah, so I was astonished to see to implement everything within this 2 layers. But IEEE does it using just 2 layers.
Yes, sir.
For their ordinary communication technologies like Bluetooth, Zigbee, or Wi-Fi. Okay, so these 2 layers are sufficient. Physical layer and MAC layer is sufficient. But when they went for the same method to implement WiMAX, things got. I mean, to me, it wasn't at, well, I mean, well organized at all. Okay. Um, I mean, at some time I uh, studied the WiMAX specifications a lot, but I didn't feel good.
Is this
Yeah,
is this the reason for lack
for
of?
for their fall,
Yes, sir. For the WiMAX, because
I
no one actually uses WiMAX now, as far as I.
yeah, it is a dying technology. I'm not sure, but let me tell you that the technology has to grow. Uh, that in incorporating many different features and expand. Okay, I mean this technology is a vast technology, cellular communication, and it has to keep growing. You have to let it grow. You have to let it incorporate many different features in the course of time, and you have to let it expand the capabilities. Okay, all different type in on different all different types of uh, res, respect. Okay, its different aspects have to expand. So if you really need this kind of expansion in different respect or addition of features, then from the very beginning, from the scratch, you have to make things well organized. Then you can let it grow that way. And 3GPP is the best in this respect. It is the best organized technology. Okay. 3GPP2 lacked, uh, and also WiMAX was even poorer example in terms of how well organized you think, how well organized things are. Okay. Anyway, so there are multiple reasons, but it is one of them. It is one of them. I'd say it is the second reason, and the first reason is like the I mean Qualcomm was not uh, Qualcomm was not a I mean Qualcomm has always been successful in the deployment of the cellular technology that gets the market, and Qualcomm had no participation in WiMAX. Okay. So Qualcomm is I mean it's an amazing company. They have amazing type of uh, I mean the way they contribute here is a little different. Okay. Uh, so their approaches, all these things are a little different, sort of unique. Okay. So many companies really jumped into WiMAX. I mean, when WiMAX started going, I was in USA, and the first deployment in of WiMAX was in South Korea. It was then called Wibro, okay, the first version of WiMAX. So when I was there, Wibro was implemented only in South Korea, but WiMAX just started its deployment. So I had to work quite a bit actually with WiMAX. But this, uh, you know, I mean, Qualcomm, and I was just thinking that, well, so many people are now started working in WiMAX area, but Qualcomm is not. So is it going to happen now that after, I mean, almost 3 decades, Qualcomm will, after like couple of decades, Qualcomm will lose the market of cellular communication? Is it, I mean, will there be any change of this kind? But, that didn't happen. Rather, WiMAX failed. Qualcomm retained its position in the market. Anyway, now in layer 2, there are 3 sublayers: MAC, RLCP, DCP. And above that, you have IP. And above IP, you may have TCP or you may have UDP. Okay, there are 2 options: TCP or UDP. So they didn't mention anything because there are multiple options. Also, the other session layers, presentation, this type of layers are not very important for us. But the application they showed, because it is, I mean, that it is like a software or something that you also have at the user device. Okay, at the user device on the other side. So you have some human level understanding for the application layer. Okay, and you are connected to up to layer 2. You are connected to E node B, but your base station doesn't understand IP packets or IP headers. It doesn't understand. Serving gateway also, I mean, it's a router, but they don't route using IP address. I mean, there's a they just route the packets. I mean, from here, from PDN gateway, you route using IP address. So PDN gateway understand the IP address. In the control layer, again, you have similar kinds of layer 1, MAC, RLCP, DCP. Okay, but above that, there are 2 other layers: RC. Okay, there's a third layer in eNode B. You don't have it here, RC. And MME has a layer NAS, which communicates with the NAS of the U side. The term NAS I didn't mention here, but I'll write down. I will show it in the writing pad. The bottom layers, layer 1, layer 2, and layer 3. Okay, we had them within the radio access network on the eNode B side. You also had layer 1, layer 2, and layer 3. Okay, the names were like physical layer 2 had 3 sublayers, and layer 3 was RC. But they were within the radio access network. But above that, you have some NAS. Okay, another layer. Now this part, since you have activities within access stratum, and here you have MME. Okay, so MME is a part of core network, but here you have RAN, radio access network. So these layers are also called access stratum, or in plural access strata. Okay, in short, AS. Just because all these layer activities will lie within the RAN, radio access network part. But above that, you have some activities with the core network that's not a part of RAN, so it is called non-access stratum. Or NAS. So that's what you have here on the EV side. So on the MME side, you have the NAS layer, because there will be always peer-to-peer activities. So you have a connection with the NAS layer of MME. So in the MME part, you have to implement some activities here, which will working together with the NAS of UV. Okay. At this juncture, I'll tell you. Any questions on this part? Okay.
No, sir.
Okay. At this juncture, let me tell you that really the development are done separately for different layers. Like there are different group of people who develop different parts. Okay. At Qualcomm, the group, okay, who worked with RLC. Okay, for example, the group who developed RLC layer. Okay, I mean Qualcomm developed the chipsets for EV. You know, if you have a good phone, then you can break your phone and you'll find the chipset built by Qualcomm. So all these layers are, yeah.
So different cell phone has different chipset, right, sir?
Yeah, it is. But
Like Motorola has different chipset from Nokia.
Right. But I said the good phones. Okay, the good phones like say Samsung, LG, and Sony Ericsson. Okay, all the good phones. They're good quality phones. Had chipsets from Qualcomm, but their cheaper phones had chipsets from other vendors. The best quality chipsets are from Qualcomm in the world, and it has been the case from the since the beginning of cellular communication in all this, over the last 3 decades. It has been the case. Samsung later developed their own chipset. So they have now phones with with both types. Some phones have chipset from Qualcomm, and some use their own developed chipsets. So Samsung, when you buy Samsung, you can check which kind of chipset you have in that particular model. Okay. The Samsung phones we have in our country use actually the chipsets built by themselves. Okay, the good quality phones. I'm talking about the very good quality phones. Okay, for
Yes, sir.
Samsung. But in other countries, you'll find those models with Qualcomm chipsets. Okay.
Yes, sir. Samsung produces 2 types of mobiles.
Yeah. Anyway, so there's a separate group of people, okay, who develop the codes for say RLC. Okay, we have a layer RLC, right? We have a layer RLC. So they develop codes for this RLC part. So there is a group of people, and the codes they generate is a set of code files. The names of the files has a part RLC. So you can identify from when you download the whole, it's called firmware, okay, that is loaded on the chipset. Okay, they have a release of a new firmware every week. Okay, every week they release new firmware. Right? I mean, within themselves, within the industry, they update their firmware. They keep working. Continuous development is there. So anyway, and when you download, you can I saw this whole bunch of files, and you have a whole set of files, maybe like say 20 files. Okay, almost yeah, around 20 files there were with with some RLC as a part of the name of the code files. So these files are developed by that group of people who are dedicated for RLC. Similarly, Mac is RLC is the simplest part of among these layers. For other layers, you have higher number of files, and the files are also larger. Okay, you have more complicated codes inside. So there are different groups of people, and of course there is interaction between the groups. Okay. So now you probably realize that this type of layering is not just virtual, okay, not just conceptual. Really, the development works this way. Separate group of people. The course also have, terms or titles with the layer as a, a part of the title is the layer name. Okay, so easily you can identify that this one belongs to that layer. Okay. Yeah, go ahead.
So this firmware, this chipset, these are closed source technology, right, sir? Like public don't have access to this files, how this works in detail. Right. It belongs to that company solely.
Yeah. But when you update, like there is a system update, right? On your phone, sometimes you can do a system update.
Yes.
Okay. Sir. Then you actually update the firmware. Okay, but it is built in. Yes, it's you load it on the chipset. You load it on the chipset, that you can also update it.
So
they call it build. The firmware is a common term. When basically firmware means the software that you load on a chipset. Okay, it is called firmware. Okay, but its technical term is build. People, within Qualcomm, they don't call it firmware. They call it build, and every week there is build with new number. Yeah.
Sir,
the question?
Well, not question, sir. I was trying to share an information. The chipset of Motorola, when they deployed GSM technologies, their file was leaked by an insider. So some European companies took those files and tried to open source the technology.
Okay.
The chipset.
Okay. Yeah, sometimes.
Yes, sir.
Sometimes it may happen. Okay. Okay. Now, this the activities of RRC and NAS in the control plane will be most important for us, because here you just route your data, and if we we have few things to understand here. Of course, we'll be discussing. Okay, but it's the way it is how you handle the user data. But in terms of control, there are many different things the network is doing, the phone is responding. Okay, there is continuous negotiation, a lot of things. So those part take up the challenges. Okay. So there you'll see that the EV and the E node B has all activities with some master control from the RC layer. RC has control over layer 1 and different sub layers of layer 2. Is the master layer for, I mean, in the control layer, I mean, in the within the RAN part. Okay. For this purpose, as I said, that there will always be peer-to-peer communication. Now, for RC, there are separate messages defined for communication. Okay, and these are called layer 3 messages because it is the third layer, right? In the control plane, is that, I mean, when I drew it on the writing pad, I mark it layer 3. Layer 3 messages or RC messages. And their messages, I mean, these are just fixed messages. And some of the messages, I mean, some messages are just defined to flow from EV to E node B, or to flow in the uplink, and some are defined to flow in the downlink. Okay, so there's, I mean, when they define the message, they also define which way it should flow. And so let me write down. Oh, sorry, I think I could. I'm not still good at. I think I could remove the screen. Okay. Why did I have to? Yeah, sorry. This way. Okay. What was I talking about? Oh, layer 3 messages. So layer 3 or RRC message. Okay. Now I said that 36 series of 3GPP define the specifications. So if you download today 36.331, okay, if you have problem in downloading, then I can help you. But please try it today. Okay, go there, go to the 3GPP website and try to download this 36.331. And this is the most important specification for us. This one is dedicated for this layer 3 RC layer. And once you open it, you will find, I mean, if you go through it, you should be able to find out different RC messages defined, many different messages. Okay, and you will also find at the top of the specification of the message which way it would flow from EV to E node B or E node B to EV. Okay, it will tell you which way. And you'll see that a particular message has a title or name of the message and at the top, and then it will give you a list of many different fields. Okay, and also what may be the different values possible for that particular field. Okay, so today at least this thing you can find out. It can be your homework, just download it. You will find out different versions for different releases like release 12, 13, 14, for all previous releases, you'll find the versions available. You see that yeah, under one release, there are multiple versions available. You can try downloading the latest one, but if there are any comments, there is a, sometimes some versions are not very stable, or there are, okay, so if there are any comment, you may not download that version. You may just download the one before that one. Uh, uh, some of the messages will be like, so for example, be like the network, the base station broadcasts some messages, keeps broadcasting, okay, some information. It always keeps broadcasting. These are called system information messages. System information. And when the message is sent in some block, a packet of message, okay, so they call it system information block, or in short SIB. So if you search with system information block, you can get to those messages in this specification. Do it today. Okay, download and search this way. Then you'll find that there are many different SIB, or system information message, SIB. Okay, many different SIB messages defined in the specification. SIB1, SIB type 1. SIB type 1, SIB type 2, okay, on and on. Now there are up to, the last specification I saw had up to 24. Okay, it may be, there may be even some additional numbers already. But last time, as far I can remember, there were up to SIB type 24. And when I was writing my book, there was up to SIB type 13. Okay, until release 9. Okay, so my book discusses up to release 13. For example, really, SIB type 18, okay, has the purpose of D2D, device to device. In the last semester, we discussed some device to device operation. That there is something called device to device operation. The two phones can communicate or transfer data between themselves. Okay, so that is called device to device. Do you remember D2D? I talked about, yeah. So that has been, SIB type 18 defines something only for this D2D operation. So most of the SIB type 2 has a specific purpose, just one specific purpose. And it was added in release 12. Okay, release 12 added this D2D operation. So SIB type 18 was then added. So newer releases add newer SIB types. Now you can probably feel that there is a provision. There is an organized provision to let it grow, to allow the addition of new features. Okay. New SIB types, if you require, you can add to convey the necessary messages. Okay. Okay. So please try looking at these different SIB types. So that's about RRC or layer 3. I say that the messages are called layer 3 messages or RRC messages. Okay, and there are some fixed messages with some fixed titles. Only those messages can flow for some specific purposes. Now, above that, you have NAS operation. For NAS also, there are some fixed messages. And those messages you can find in some other specification books. In the specification books, actually, there are, NAS type, well, the same type of NAS operation you also have in 3G. Okay, so the series like 24 series, okay, has a lot of specifications about NAS. Not in 36. There are commonalities. Okay, so anyway, but the point is for NAS also you have some fixed messages defined in the specifications, and they flow. But you see, whatever NAS messages flow between EV and the MME, they have to flow through the base station, because you have the MME behind your base station, So the way the NAS messages flow, that there are certain RC messages. Okay, 2 RC messages are defined, which are empty. We just have header, but no other information. And these RC messages just load NAS messages. When you need NAS messages to flow, then the empty RC messages carry the NAS message. So these 2 RC messages have no other purpose but to carry NAS message. When you need to send some NAS message, okay, from the phone end to the MME, you use the RC message that takes the NAS message in the uplink, empty RC message. So the NAS message you load on the RC message and forward it to eNode B. The eNode B, when it finds that RC message, okay, it knows that it is just for the purpose of carrying the NAS. So it just separate the NAS message and forward it to MME. Okay. Similarly, when the MME needs to send some NAS message to the EV, it uses that, it sends the NAS message to the eNode B, and the eNode B loads that NAS message on a RC message, which has the only purpose to carry the NAS message. Okay. So the eNode B loads it on the RC message and sends that RC message to the EV. The EV removes the RC header, and this RC layer removes the RC header, extracts the NAS message, and forwards it to the NAS layer. Okay. So that's how EV and the MME talk to each other. Although the communication at the lower stage you have between RC, but actually there's a communication between the NAS layers. Okay. Now, any questions so far? Few things we are skipping, like these communications, how you have the layer, the protocols that work in some layers. Well, these are just to implement a communication between eNode B and MME. Okay, and there are it's a wired network a lot of times. Okay, so you have some protocols to implement that kind of communication to transfer just the information, but the actual activities you have here are within these links, it is only here. Okay, but other layers are just assisting the flow between the communication between E node B and MME. That's it. Now, OFDM is a new technique. Okay, now it is not new any longer, but it's the newest or is the latest deployment in cellular communication in terms of multiplexing technologies. In this case, you use a number of carriers for simultaneous transmission. Okay, instead of using just one carrier that you had in all the legacy technologies 2G or 3G, use multiple carriers together. And since you have multiple carriers, they are called sub-carriers. Just because you have multiple carriers, they all work. I mean, they have enough. I mean, they are not lacking anything. Although you are calling sub-carriers, it's not like that. They are less capable or something. They transmit the bits or symbols. Now, all these sub-carriers are synchronized. When you transmit using multiple sub-carriers, you send symbols together. Okay, I mean, you time synchronize the symbol transmissions on all the subcarriers. Put all the subcarriers on different subcarriers in one symbol period, and then in the next symbol period again put symbols on all the subcarriers, on and on. So you have some parallel streams onto the subcarriers. The subcarriers are made orthogonal to each other. Well, what kind of orthogonality do you have here? Well, by orthogonality, you mean here that you don't have interference among the subcarriers. Okay, like the cross correlation is 0, and you call it orthogonal. That means one of them does not disturb the other. Okay. You can have independent operation when you are operating both. It is like you operate. It will be in terms of the effects. You have it. It will be the same when you operate only just one of them. Okay. If you have two users in the CDMA, okay, on two OVSF cores, then as we showed, if we ignore the background noise, okay, then actually the users say A and B don't disturb each other. So now if you stop the operation of A and let only B operate, then B has the same kind of experience. So you may have say 10 users, but if they all are orthogonal, then nobody disturbs others. So if you stop the operation of 9 and let just one operate, you have the same kind of outcome. That B user experiences the same as if when he's just he alone operates. Okay, the experience he has is exactly the same, not exactly, okay, pretty much the same as he has with some other orthogonal users. That's what you mean by orthogonality or cross correlation, zero cross correlation. Okay, stopping the operation of others don't change the experience. Similarly, here, by orthogonality, mean that you have multiple carriers, but if you just had operation of one carrier. Okay, you might your experience might be very good. Now, when you add the operation of other subcarriers, you have the same kind of experience. Okay, so then actually you have no disturbance from others, or actually you don't have interference. Like, right, the term we use when you have in the frequency domain, the term we use interference to indicate the disturbance. So you have zero interference. It's not exactly zero, but it's very, very low. So that is called inter-carrier interference. I mean, between two carriers, you have interference. Okay. So theoretically, it is really zero. Like theoretically, you have zero cross correlation among CDM users. But how do you make it? Well, there's some mathematical proof which shows that if you choose a subcarrier spacing, the spacing between two subcarriers equal to the reciprocal of the symbol period, then what happens? You get things like this. See, if I take the example of this green one, I have this one, this line, the main center, okay, of my transmission. I'm sending a symbol using this carrier. So I have a center frequency, right? This is the center frequency. Well, as I deviate from the center frequency, the energy reduces. Well, now the energy as keeps reducing, it falls to zero when you get to the center frequency of another carrier, your next subcarrier. Okay. I mean, at the center frequency, okay, actually that is called the subcarrier frequency. Of course, your transmission occupies a range of frequency. It is never a single frequency, right? Whenever you transmit some information, even if it is a single symbol, you must occupy a range of frequency. And but that is the center. So that center we are calling subcarrier frequency. But these subcarrier frequencies are related in a way that the energy of all other subcarriers, energy from all transmission on all other subcarriers becomes zero at the center frequency, at the subcarrier frequency. And that is true for all of them. Take any example, like say the green one takes on a zero value, okay, at this subcarrier. And then again, here the energy keeps growing, but again it comes to zero. Where? At the center of another subcarrier. Here also it gets zero. So the contribution becomes zero at all center frequencies from other transmissions, from neighboring subcarrier transmissions. Okay. So it is. So this is how we can conclude that the center frequencies have no impact from other transmissions, and so we can call it orthogonal. Call all the center frequencies orthogonal, or the subcarrier frequencies orthogonal. And we can also say that okay, the center frequencies have zero inter-carrier interference, ICI. Okay, interference among the carriers. I see. Well, but that does not solve all problems. Like, I have a whole range of operations. So if I think of the transmission of the green, it is not just you are transmitting on this particular frequency, rather it takes up a whole range. Okay. And as I take, say, this point, I have some energy from this blue one, or I take this frequency of this green transmission, I have some energy from this red guy. Okay, so neighboring transmissions have some interference. Okay, well, the answer is that interference is bearable. Let me show you how. Well, I wish I could be good at drawing. I'll try to draw that the same kind of figures and oh, sorry. When it comes to 0, you have another. And then you also have okay. Does it look like an elephant? How well did I draw?
Sir, it is a good drawing, sir.
Oh, really?
Yes, sir.
Okay. I mean, do you think that I mean, that's the way you can get good grades from me?
Yes, sir. Even if it is 1 mark increase, I think it's a benefit.
Okay, okay, okay. Now you see that this blue one definitely has some energy. If I think of, say, this point, some energy from the green guy, or this point from the pink guy. But if I take, say, a good range of the blue one, say up to this range, okay. So this range, up to this range of bandwidth of the blue transmission, the difference between energy, okay, the desired energy, this is the intended energy level, the blue one, and this is like undesired energy level, right? There's a good difference. There's a good difference, right? I mean, when I take just the center, then I don't have interference at all. But for other frequencies also, up to a pretty good range, I have very good difference, and I need actually a good ratio of CINR. Okay, it doesn't have to be, it doesn't have to have 0 for your interference or noise. Okay, you don't need to have this part 0, and it is actually never 0.
Yes, sir.
Okay. It never becomes 0. And it doesn't have to be. So it just have to be low enough. Okay. Or I mean, so low that you can tolerate. So it is, if you look at the difference in the energy level up to a good range, it looks tolerable. The difference between the energy level. Okay. So I mean, use this viewpoint of comparison in this better picture now. Now you look closely at this figure and try to have a comparison. Really, we have a good difference in the energy level. and so it works. So up to say this point, it is usable, right?
Yes, sir.
Okay. So that is how things work. And so you see that you have some green part up to this part and from here it's the frequency range for the blue part. Then okay, this part will be the red part. So you have frequency ranges for different subcarriers one after another, and it appears that you don't need any margin one after another. You can, once you have the frequency range of one subcarrier, right there the you can use the start frequency for the next guy. Well, practically you need a very I mean slight margin, but ideally you don't need any margin, and this is the reason WebDM has become so popular. The advantage of WebDM that you send your data on multiple subcarriers, then you can experience flat fading. This is the key advantage, and this is something we discussed in the last semester. But it could be a question whether or not this advantage had been known to all people. Okay. Well, it was known before. People always had the understanding that if I split my data and transmit together onto multiple carriers, then I can enjoy small bandwidth, and which leads to flat fading. Okay. This frequency selective fading has always been a really nagging issue for RF engineers. So I can enjoy flat fading, but people couldn't do that. People didn't go for this type of use of multiple subcarriers, because when you do that, you need to use some margin. Otherwise, there will be interference between your carriers. So normally, if you don't use OFDM, or meaning that if you don't maintain this relationship, then what happens? I mean, you don't have this kind of orthogonality. And then to make sure that you don't have inter-carrier interference, or to avoid ICI, you need to allow good amount of margin between the carriers. And that will cause too much wastage. That wastage will overpower all other advantages. Okay, I mean, that wastage will overweigh what you get out of the flat fading. So this is why people did not go for splitting data and transmission on multiple subcarriers until WebDM was invented. But WebDM was invented with the solution that there would be orthogonality among the carriers, and so you can use now without any requirement of margin, or with the use of nominal margin. Okay, so theoretically you don't need any margin, so you don't have any wastage for margin. You can just straight enjoy flat fading, and that can increase the data rate by many factors. I mean, by some significant ratio. The subcarrier spacing is like 15 kilohertz, and that I mean, from your last semester, that should match the usual multipath environment. Okay, multipath environment. But there are some, I mean, considerations both in time domain and frequency domain. I mean, although there is relationship, but it's possible that you have you try in both domains. But in the frequency domain, you should keep the subcarrier spacing fixed for your technology to ease your implementation. When you use a fixed subcarrier spacing, then your RF circuitry will be simple. And so that is held fixed for 15 kilohertz, held fixed at 15 kilohertz for LT. So LT uses 15 kilohertz. Okay. So there are some, variations in the recent specifications in 5G, which I'll talk about later. But in 4G, it is always 15 kilohertz. But in 5G also, it is for some special cases. However, for something called MBMS, the subcarrier, it is also possible that you use the subcarrier specifying half of that, 7.5 kilohertz. MBMS is something which has not been popular, but in the past there was a lot of activities with MBMS. It was just some mobile TV channel technology. Okay. So it was the understanding that each base station will operate with a number of TV channels. So they'll just broadcast. The operation will be only in the downlink. Okay. So broadcast TV channels, say sports channels, cartoon channels, there'll be many different channels available. So you'll be from your phone, you'll be able to just choose one of them and enjoy it. So just it was TV. MBMS was, it has the purpose of mobile TV, and similar technologies were some also there, especially in Asia Pacific region. Okay. Japan, Korea, they had implementations of some technology, independent mobile TV. I mean, they are not a part of cellular communication, but some independent mobile TV implementations were there. I think they still have them, but at some point there are a lot of activities for this kind of development. But nowadays, uh, YouTube has become a solution for all these things. Okay.
Yes, sir.
Yeah. So it has become a better choice. Okay. So it has been solved from the application layer instead of for MBMS. I have a separate chapter, chapter 24, has a detailed discussion on MBMS. There's a whole lot of different uh, type of implementations at different layers for MBMS, with the provision for many different channels operating together. But I mean, I think if I release another version of my book now, I don't need to include this MBMS. Okay. Okay. And I mean, if I explained MBMS, then I could also make it clear why a smaller subcarrier spacing would be helpful for MBMS operation. Okay. But I'm not doing that, so it's just something I mentioned, that what are the provisions. So it is 15 kilohertz, okay, for LT. Now I think it is almost 5, right? Oh, it is 5.
Yes, sir.
Okay. Any questions so far?
No, sir.
I really had a plan to go further, but we were discussing some Qualcomm implementations and all that, so it killed a lot of time. Inshallah, I'll be more organized from the next class, and we'll be able to go faster. Okay, we'll be able to cover a larger part of our regular class notes. I've already uploaded, I think, up to lecture 6.
Yes, sir.
Okay, so I'll see you tomorrow. Any questions?
Sir, it will be better, sir, if you upload today's online lecture as soon as
I
possible.
will, inshallah. I'll do it right after I finished the class today. Anything else that I can help you with?
No, sir. We can
Okay.
conclude.
Okay. And sometimes I joke in the class, but I'm not sure if you could get the joke or not. Okay, it's
No, sir,
really
we get most
uncomfortable.
of- We
I
get
mean,
most of your jokes, but we mute ourselves so you can't
okay,
hear our laughs.
okay, that's good. I mean, it would be uh, the most uncomfortable for me if you, I mean, didn't fail to understand the jokes. Anyway,
This is the problem of online class. In
yeah,
physical class, we could have
right,
laughed in front.
right.
Okay, sir, we'll laugh from now. After I am muting us.
Okay, okay. Thank you for your time.
Thank you, sir. Assalamu alaikum, sir.
Assalamu alaikum, sir.
Walaikum assalam.